In this lecture, we're going to introduce the basics of signal notation and several properties. We'll begin by defining signals as mathematical functions, and then proceed to look at continuous and discrete time signals, followed by a definition of what it means for a signal to be periodic. Now recall that a signal describes how some physical quantity varies over time and or space. So it could be the pressure that's being received at this microphone, for instance, and how that varies with time, which conveys my voice. So on the lower left here, I have an example of a signal where along the axis we have the time variable, and so we see the amplitude varies with time. And on the right, I have a picture of the moon, and this shows how the signal is varying over space. Well, mathematically, we can describe signals as functions. And they'll be a function of one or more independent variables. We have multiple independent variables in cases where we have a signal that's defined over space, such as here u and v, and if we were to add movie, then we'd have spatial position as well as time. So you can get more than one independent variable. In this case, t on the left or u and v on the right are defined as the independent variables, and then x is the dependent variable because the value for x depends on the value on where the independent variables are chosen. Now the independent variables can be either continuous valued or discrete valued. In this graph I'm showing an example of a continuous valued independent variable because the independent variable t can take on any value along the axis. In this next example here, we've got a discrete independent variable, and in this case n is limited to a particular set of values. In other words, it's not possible to look at n equal 1/2 because we've got n only on the integers, and it's only at those values that the dependent variable x is defined. So it doesn't mean anything to say x of 1/2 because there's no value there. So this is a discrete independent variable, and typically for simplicity we will restrict our discrete independent variables to be defined on the integers. Now for notation, you may have noticed this already, we're going to use parentheses to represent continuous independent variables, and we're going to use brackets, square brackets, to denote discrete independent variables. And that'll be true whether these are functions of time or frequency or other quantities. Okay, if you have C square brackets, you know that it's a discrete independent variable, and those are going to be limited to indices of integers. Now we can obtain a discrete independent variable signal from a continuous time one through the process of sampling. Okay, and that's often where these come from. So what I have here is a block diagram showing a continuous time signal. It's defined as a continuous function of time, such as the pressure at this microphone. And then what we're going to do is we're going to define a discrete time signal by sampling the continuous one at intervals of n times capital T. So I can write that in block diagram notation here, or I can write it mathematically as saying that my discrete time signal x of n is equal to the continuous time signal x of t evaluated when t is equal to n times t. And that gives me x of, we'll note the parentheses here, x at n times cap t. So n is my discrete valued independent variable, and you can see that it's defined on 0, 1, 2, 3, 4, and so on. And the amplitude of the dependent variable is given by the sample of the corresponding continuous time signal. Now what I'm illustrating here is something that we might call an analog to digital converter, and that's the essence of converting from continuous to discrete time. Another example of sampling is a digital camera. Now this is not a time signal because we're sampling in space, but there's a sensor chip that has a bunch of little light detectors that convert this signal that's defined as a continuous position of space to one that's defined at a series of pixels. Okay, so that's a digital camera, also does sampling. Now, any signal that's stored in a computer must be in discrete format, must have a discrete independent variable, because we can only store sequences of numbers. However, oftentimes it's useful to display signals as if they were continuous, and in order to do this, we might connect the samples of our signals with straight lines. Okay, in MATLAB, the software that we're using here, and I'll display in a moment, does exactly that when you give it the command plot. If you give it the command stem, it will draw a series of discrete stems, which is our explicit notation for a discrete time signal. But usually it's convenient for visual clarity, especially when you have a large number of samples. If you have 50,000 samples, it's pretty hard to draw individual stems and see the details of what's happening. Whereas if you connect the samples with a straight line, you get a much better picture. And you can also then label the time at which each sample occurs along the axis so that it gets visualized as if it is a continuous time signal, even though it's a discrete set of samples that you put into the computer. Now, one of the important properties of signals has to do with being periodic. And a signal that repeats the same pattern is said to be periodic. So down below here, I've drawn a discrete time signal, y of n, and a continuous time signal, z of t, and both of these repeat a pattern. Okay, the y of n has two samples at 1, then two samples at 0, then two samples at 1, then two samples at 0, and so on, whereas z of t has this flat, drop, and then a negative ramp and a positive ramp, and that pattern repeats forever and ever. So the period of the signal is the interval over which it repeats. So in this case, we can define this mathematically by, as shown in this series of equations here. So if I take a continuous time signal and it has a period, that means that there's some interval t naught where if I shift the independent variable by that, I get exactly the same value of the signal. So if I took z of t here and I shifted it by 2 units, I'd get exactly the same signal. And the mathematical definition of periodicity then has to hold for all possible independent variables t. Similarly, in discrete time, if I take my signal x of n and I shift it by some interval capital N, and I get the same signal for all little n, then I'd say that's periodic as well. So you can see here, if I took this signal and I shifted it by 4 units, I would get the exact same signal. So that's also periodic. The period in the discrete time signal then is going to be 4 or 8, it turns out. I can also shift it by 8, or I could also shift this by 12 and it would perfectly line up, and you see that any multiple of 4 will give you the same signal. In my continuous time example, if I shifted by 2, or I shifted by 4, or I shifted by 6, I would get exactly the same signal. Now, the fundamental period is the smallest repetition interval. Okay, so that gives us a unique description, and in the discrete time signal, that would be 4, we'd say is the fundamental period of y of n, whereas in the continuous time signal, we'd say 2 is the fundamental period of z of t. So we're going to look at a couple example signals here, a saxophone playing 2 different notes, and then a speaker saying the word 6. In this figure, I'm depicting an A, the note A, played by a saxophone. And what we have on the top is about 2.5 seconds. So this is units here are milliseconds. So this is about 2.5 seconds. And you can see it was silent, and then the note began, and then as we get to the end, the note ended. So on the bottom panel, we're plotting a section of this note from about 500 to 570 milliseconds, so right in this interval here. And what you can see is that this signal looks very periodic. Okay, it repeats almost the same pattern on a pretty fine scale. In fact, if we zoom in, we'll see that the interval over which this signal repeats is about, let's say here we're at 523.3 seconds, and here we're at 525.5. So it's about 2.2 milliseconds is the fundamental period of this signal. Now I want to point out as well that this signal was played by the saxophone into a microphone, and then an analog to digital converter was used to convert that from the continuous time pressure fluctuations at the microphone into a series of numbers that we could store in the computer. Now, the signal is sampled at the CD sampling rate of 44,100 samples per second. So in this interval here that it's on, we've got over 100,000 samples. And so we're not displaying this as a stem. In fact, even plot, where we're connecting the lines, gives a strange shape because of the effect of the graphics. Okay, but down in the bottom panel, you can see that the signal resolved more cleanly, and these are just a series of lines connecting the points of the signal, even though it's a discrete time signal in the computer. Now the next one I want to look at is, before we go on, let's play that note for you so that you can hear it. This is the sound of the note A on the saxophone, which you're just looking at. Okay, now I'm going to play another note, a D flat, which has a lower tone to it, and then we'll look at the waveform of that. So here's the sound of the D flat. Okay, so let me go back to the A. Now the D flat. And so here the waveform for the D flat. And once again, we're depicting in the top panel about, in this case, the D flat lasts a little less than 2 seconds. And if we expand the section between around 500 milliseconds for a few, I'll say up to 568 or so is what I have here, we see that this signal is also very structured and highly periodic. Okay, it looks like it repeats, and indeed it does. Now, mathematically, this signal would not be defined as a periodic signal in the strict sense of the word, because you can see that it was 0 and then it turned on and it went back to 0. So over all time, which is what the mathematical definition says, this signal does not repeat. But in a practical sense, it definitely appears as a periodic signal when the note is being played in a steady condition. Okay, so the mathematical definition of periodicity serves as a very good model when we consider a limited interval of the signal. And in this case, remember the tone of the D flat was much lower than the tone of the A, and if we look at the fundamental period of this signal, we see that, we're here at about 531 milliseconds, and then the next period is 538 say 2. So that comes out to about 7.2 milliseconds. So the fundamental period of the D flat is much longer than the 2.1 millisecond fundamental period of the A by more than a factor of 3. And that's apparent in the tone of the lower note that we hear for the D flat. Well, next let's look at voice, human voice, with the spoken word 6. And what we have here is a recording, and the first part is the S sound. We got S, and then we have the I, the I, and then the X sound. Okay, so this is the word 6. And in fact, let's play that before we go further. Here's the word, spoken word 6.
6,
Again.
6,
Okay, so if we look at, this is produced by a human speaker, so the waveform is fairly complicated, and again, there's a lot of samples in here. I believe this was only sampled at 32,000 samples per second, so we've got about almost 700 milliseconds of samples here, so this is probably on the order of 20,000 samples. And if we zoom in on some sections of these waveforms, let's zoom in on the S here. We see that it's got a lot of variation, but doesn't appear to be any obvious structure in this waveform. And that's consistent with how the sound is produced, because when you make an S sound, you're putting your tongue up by your teeth, and the airflow ends up flowing around those obstructions, and it has a turbulent character to it. So we wouldn't necessarily expect a very periodic structure or repetitive structure with this part of the sound. Let's zoom in on part of the I sound here. Now this sound is produced in a different manner than the X, because if you think about it, most vowels have a resonant character to them. So what's happening is you're exciting your vocal tract, and it's the resonance of the tract that produces the sound. So you have I, and that leads to a much more periodic or repetitive type signal, similar to the saxophone. Now the saxophone is creating somewhat of a mechanical resonance because of the nature of the device, and we looked at notes that were playing in a steady state condition. So the I, although it's resonance, it's a human, and it's not a mechanical system. There's biology involved, and also it's in the context of a word which the tone is changing. So, but even nevertheless, we can see here that the character of the signal tends to be repetitive. You have this initial rise, then large negative value, then large positive value, and so on, and then these other oscillations occurring later, and then that repeats. And the period is approximately, let's just go from this negative peak here, this looks like it's occurring, let's just round off to 314 milliseconds. And then this one here looks like it's about 323. So that's about 9 milliseconds for the period of the sound in the word I. And again, this would not satisfy the strict mathematical definition of periodicity, because these waveforms aren't exactly the same. But nevertheless, the notion of a periodic or repeating pattern is a very good model for this particular I sound. So looking at the X sound, again, if you think of X, it has a lot of the similar attributes as an S. Much of that is formed by turbulent airflow over the teeth, and if we zoom in here, we see again fairly high frequency fluctuation, but there doesn't appear to be any obvious patterns. Well, let's conclude then. And what we've looked at in this lecture is that we can treat signals as mathematical functions, where we have an independent variable and a dependent variable. The independent variable can either be continuous or discrete valued, and most natural signals in the physical world have continuous valued independent variables. But once we get them into a computer, we sample them, and now they become discrete valued signals. Whether or not a signal repeats, it turns out to be a fairly important property. We'll see as we go on with this material. And from a practical sense, there's a couple issues. One is that when we're displaying signals in a computer, once we've got them in the computer, they automatically have discrete independent variables. So we have to sample them to get them in there. But for display purposes, we may choose to connect the dots, connect the samples with straight lines or otherwise, and thus present a visual picture as if it were a continuous independent variable. And the other practical aspect is that the mathematical definition of periodicity implies that the signal repeats forever. And in practice, there aren't any signals that repeat for all time or all space, but locally, this idea of repetition is a very good approximation to some local interval of time.